Hello AP Calculus students, Mr. Record here from Avon High School, and we wanted to do a quick little video here that will introduce one of the main components of the second part of Calculus 1. That's kind of the development of the integral. And before we do that, we start talking about this idea of area. But prior to doing that, it's sometimes helpful to have a little bit of a refresher course on basic usage of summation notation and how some various formulas and properties can help us break apart these such summation notations. So we're going to jump right into a few examples here. And our first example just gives a very quick um, formula, I guess, if you will, for the summation of a subscript I. And you'll notice that I've got the various portions of this summation expression identified. I've got the index, which is typically the letter I, sometimes J, sometimes K is used, but that's always going to appear at the bottom of the summation symbol. We're going to have a lower bound, which doesn't have to begin with 1. It seems logical often that it would begin with 1. Most of our problems will begin with 1. But like I said, it's not obligated to do so. And then you have an upper bound that quite often is going to be something numeric, but you're going to start to look at other approaches to these summation expressions where that n can be a little arbitrary. Because basically the idea is that you're going to take this index starting at its lower boundary and you're going to insert it in for the letter I in this expression. And then you're going to add the next term, which is where this index increases by an integer factor of 1, and you're going to plug that in, and so on until you reach this upper bound, which is going to produce the very last term, in this case, a sub n. So you've got a really easy pair of examples here in example 1. The summation of I, as I goes from 1 to 6, is just having us add the numbers 1 plus 2 plus 3 plus 4 plus 5 plus 6. It might seem a little laborious to write it out this way, and there are other ways that this can be tackled. But since there are only 6 numbers to add, something that's pretty simple to do, we can kind of group these. There's 10. These two would make 8 more, so there's 18, 19, 20, 21, and then we're off and running. Now when you look at B, B is going to be a little bit more, I guess labor intensive, for lack of a better word. So clearly one thing that we can do is adopt a similar approach that we did in part A, and we could allow J to start at 3 and run J in, a 3 in for J that is, and get 3 squared, and then go to our next integer increment where J is 4 and plug that in, etc., etc., etc. Now I'm not going to want to write all of these out because that's a lot of work. Nor do I want to really add these up by pencil and paper method because, again, that's going to be a lot of work. So I'm going to allow us to use a calculator, and usually just about any scientific calculator will be able to address a summation notation feature. Obviously, the graphing calculators on the market will do that. I'm going to go ahead and show you 2 different approaches to this particular problem. This one is using a TI-84 or a TI-83 type of model. And what you would do is you would go into the math entry, and you're going to have to kind of arrow down a little bit to option 10 or 0 here, summation. And if you've got one of the newer calculators with some of the newer operating systems, you're going to have sort of a pretty print approach to this, where we can just basically enter our values. J is going to run from 3 to 12, and we're talking about J squared. Oops, try that again. We're talking about J squared. In order to get the J, we're going to have to go into our numeric, or alphabet, I'm sorry, which is alpha comma. Should bring up our J, and then we can square that. And then if we hit enter, we'll have 645. Another way to do this, if you are a TI Inspire user, very similar. You would go into, one way to do it is just go into the math template. This is probably the easiest way. by pressing the button next to the 9, and you can see all the various template options you have, and there's our summation. So as j goes from 3 to 12, for j squared, we're going to get that same answer of 645. Now, that might seem sort of cheating, but there is going to be a little bit better approach to handle a problem like a j squared, where you have so many values that you're going to be having to plug in. And that sort of brings us to our very important summation formulas. Now, I want to make a distinction here. We've got summation properties and we have summation formulas. At the top of the screen here, I've got various properties listed. And these are the basic ideas of a scalar within your summation expression can come out in front, which is what property 1 is saying. Property 2 is just simply saying if you're finding the sum of two separate expressions, that is the same as the sum of the summations of those two separate expressions. If we're taking the summation of the difference of two expressions, we can just then find the difference between their separate summations like that. Now, the summation formulas that you see here in the blue box, these are the guys that really tend to make our job a little easier, especially when we have a pretty wide range of our values for I in this case. So we have the various summation formulas for the constant, for the value I to the first, I squared, and I cubed. These are the four most popular. So a side note here about a mathematician named Carl Friedrich Gauss, who actually was sort of renowned for discovering, or not necessarily discovering, stumbling upon formula number 2. It was discovered long before his time. But at age 6 or age 5, he sort of stumbled upon this particular formula while he was serving a sort of a punishment for doing something bad in his kindergarten classroom. So let's go ahead and take a look at our example 2 here that asks us to evaluate the following summation expression. And you'll notice here that since we're going from 1 to 25 for our I, we want no part of plugging in each of these numbers in for I and laboriously finding the summation. And we're going to go ahead and say that we're not allowed to use that graphing calculator. So what you're going to do in this particular situation is you're going to rely very heavily upon the summation formulas and properties. Now, the first approach to this is to probably utilize, if I go back, some of the properties. And namely, I'm going to talk about property 2 and property 3 that just simply allows us to break this summation apart. So we're going to go ahead and essentially write this as 3 separate summation expressions. The summation as I goes from 1 to 25 of I squared, the summation as I goes from 1 to 25 of I, and the summation of 4 as I goes from 1 to 25. And you'll notice that we went ahead and just plopped down the appropriate signs in between, a minus followed by a plus. And then at this point, we notice that each of our summons, and that's what you call the values that are within the summation expression, all fit very nicely with, with the formulas that we have written here in the blue box. And namely, we're going to use formula 3 to start things off with. The summation of I squared as I goes from 1 to n is n times n plus 1 times 2n plus 1 all over 6. So we got n times n plus 1 times 2n plus 1 all divided by 6. Now, you might wonder, well, wait a minute. The n value is 25. It's known. Well, certainly I could have plugged 25 in. Instead, I'm just going to do a little bit of a such that symbol at the end of this expression to denote that I'm going to plug 25 in for n. We'll do that here in just a second. For the summation of I, we notice that the formula reads n times n plus 1, all divided by 2. The purpose of this video isn't necessarily to prove these. Those can be found on many other videos across the interwebs. It's probably likely that you're going to use a proof by induction in order to take care of these, but that's kind of beyond the scope of the calculus class. And then for the summation of 4, we're just going to use the summation of the constant c, which is c times n. So that would be 4 times n in this case. And as I said before, we're just going to evaluate all of this such that the n is going to be 25. So when we do that, we end up with 25 times 26 times 51, all divided by 6, minus 25 times 26, all divided by 2, and then we have plus 4 times 25, which is 100. Now, you might be able to simplify a little bit here to make the goings a little easier. For example, the 26 and the 6, let's use a different color here. We could cancel or reduce 2 out of each as such. And then you might notice that 51 is divisible by 3. 3 goes into 51 17 times. And over here, we could go ahead and reduce the 26 with the 2. And then what we're looking at this point is essentially 25 times 13 times 17 minus 25 times 13 plus 100. And now I understand that I'm about to do something that probably is a little underhanded in that I said that we weren't going to use the calculator, but for the sheer fact that I don't want to multiply these values together, I'm going to go ahead and just type this in here very quickly. We had 25 times 13 times 17. Let's make sure that that's correct. 17. Try that one more time. 17. And then we were to subtract 25 times 13. And then just to double check, I believe we were going to be adding 100. So we'll add 100 to that result. Just one plus sign would work. And we end up with a result of 5,300, which should be the correct answer. I'm going to double check this by using the TI Inspire to ensure that we get 5,300. Let's go ahead and move over to that software. Once again, we'll go into the math template, and we'll use this option where I is going to start at 1 and move up to 25. And then our expression was I squared minus I plus 4. And lo and behold, we do get that 5,300, although much, much quicker. So as you can see, we were able to potentially bypass any kind of summation feature of a graphing or scientific calculator by relying very heavily on these formulas. Now, in the last part of this video, I wanted to run through an example where we can kind of work the opposite direction. In other words, we're going to be given a series of terms that are added together, and from that, we're going to write the summation notation that would be equivalent. So my best advice for a problem such as this would be to go ahead and lay down your summation expression and choose some kind of an index. You can use I, J, K, and then start to think about the terms themselves and what you notice to be very, very consistent from one to the next. So some of the things that we notice are consistently featured in this particular summation is the fact that we are adding fractions. So you can put a fraction bar. If you look at the numerator, you'll notice that each time the numerator is 5, so that's something that's constant, that's not going to change. The denominator appears to be the sum of two things, and more specifically, it's the sum of 1 plus something that's changing from a 1 to a 2 to a 3, which is a perfect example of using the letter I for the thing that's changing. And since we see that I can start with this 1, we'll use that as our lower index. And we can finish up with our upper index of 15. And then we've got our summation expression that's needed for this problem. Remember that your job in this particular problem was not to evaluate this, which is good because we would probably have to rely on a calculator for this because we can't utilize the summation formulas for an I that's located in the denominator. So we've answered the question. Use summation notation to rewrite. In the next and final example here, part B, we have a slightly more complex series of terms, but the approach is going to be very, very similar. So I'm going to say we're going to talk about summation. I'm going to use the letter J this time just for some variety. And then I'm going to start looking at what I see in common from one term to the next, etc. Well, structurally, I see some brackets followed by some parentheses, so there's nothing wrong with just like laying down that basic foundation. And within the brackets, I seem to start with 1 each time. That doesn't change, followed by a subtraction. And then it seems like there's going to be a quantity that's going to be squared within the parentheses. So now I have to start looking about what I see in these parentheses. Well, in the first term, I have 2 over n minus 1, followed by the second term, 4 over n minus 1, and then 6 over n minus 1. So we can see that this value on top of the n is something that's going to change, but the n is not. And of course, the subtraction of 1 is not changing. Now, as far as what do you put above that n, the universal way to depict even numbers like 2, 4, 6, even integers, is just to take your counter j and multiply it by a 2. So we'll say 2j over n minus 1 squared. And then when you look at the parentheses values after the brackets, they seem to consistently be 2 over n in this case. All right, now, the last thing that we have to do is figure out where we're going to start and where we're going to end with our j. Well, in order to produce this first term of 2, which I'm going to start to highlight here in a different color, if 2j is that particular expression, I want my j to be a 1 in order to make that happen. 2 times 1, of course, is 2. But then if I want to finish this up, where 2 times n is my final expression, then I need to think about what to start or end j with so that 2 times that value is equivalent to 2n. And after careful consideration, I come to the realization that it's not a number at all, and it's just the letter n. We'll make this happen. And there we have it, our summation expression that would be depicting this particular series. So anyway, I hope this helps. My next videos are going to focus a little bit more on what we're going to do with this newfound knowledge of summation expression in terms of finding area, and then we'll slowly bridge that to the definite integral. Anyway, I hope this helps, and we'll see you at the next video.